Welcome to Pluralsight, everybody. This is Network Addressing Basics. My name is Brandon Carroll, CCIE number 23837. So the first thing that people ask me when I tell them that they need to know the basics is, Brandon, are you kidding me? Well, the answer is no. Even CCIE candidates, even people who are CCIEs already need to review the basics from time to time and keep their skills sharp. So let's discuss how IPv4 and IPv6 addresses are, first of all, structured, as well as represented, and also how they are allocated. We'll begin with a discussion on how IPv4 addresses are structured. Now, you're probably already familiar with IPv4 addresses. Here's three different addresses. This first address, 10.0.0.1/8, you probably recognize that as a Class A address, and that would be correct. That's a Class A address, even though we're showing it to you with a /8 mask. That mask is what we call CIDR notation, but that's a Class A address there. We have 172.16.0.1 with a /16. That would be a Class B address. And we have 192.168.1.1/24. That would be a Class C address. Now, one thing that's true with all three of these addresses is that they are 32-bit numbers, and they're accompanied by a mask value, the /8, the /16, or the /24. Now, each of those mask values is actually a 32-bit subnet mask, and the number there, 8, 16, or 24, would indicate for us which mask bits are enabled or set to a value of 1. And the remaining bits would be set to a value of 0. And this is how we determine which portion of the address is allocated to the network and which portion of the address is allocated to the hosts. Additionally, we know that all three of these addresses, and really any IPv4 address, breaks down into binary numbers, 32 bits worth of binary values. Now, each bit that's inside of an octet, because that's how we represent these addresses, and dotted decimal notation, separated by the decimal points, we have an octet. Each bit that's inside that octet has a specific bit weight that is assigned to it. So if we were to just take one portion or one octet, we would break it down like this. We have bit 8, 7, 6, 5, 4, 3, 2, and 1. And if we were doing a conversion from decimal to binary, we would be responsible for figuring out which bits we would enable to equal the decimal value. So as far as the bit weights go, that looks something like this. Bit 8 is worth, or the value of that bit is 128. Bit 7 would be 64. Bit 6 would be 32, and so on. So now if we took the number 10 as an example, the number 10, we would have to enable bit number 4 and bit number 2. 8 plus 2 equals 10, so we would toggle those bits on, and the remainder of those 8 bits, or the other 6 bits in this octet, would be set to a 0, and that would represent the number 10 in binary for us. And we could do the reverse process if we wanted to and convert from binary to decimal or decimal to binary, depending on which direction we want to go. So that's how we would figure that out. The binary representation would look like this. So we can see all the bits set to 0. Now bit 4 is set to 1 and bit 2 is set to 1. And that 8-bit value there that we're representing equals 10. Okay, so that number right there equals the number 10 in decimal. So that's probably a little bit of review for you, and that's okay. It's good to do some review from time to time. Now, as a CCIE security candidate, you should already understand how to do this subnetting and binary and conversions like this. None of this should be new to you.